It is midnight on the highway. You are inside a 2-ton Mercedes, moving at 120 kilometers per hour. The cabin is quiet, the engine runs flawlessly, and the 3-pointed star on the steering wheel gives you absolute confidence. Outside, the darkness flows past in silence. Then a hard metallic crack comes from the front right wheel arch. No warning light appears. The steel perch carrying the front coil spring tears away from the body and collapses onto the tire. The car instantly yaws to the right, buries its nose into the asphalt, and lights up the highway with a shower of sparks. The steering wheel tries to escape your hands, and the cabin that represented luxury only seconds earlier suddenly becomes a metallic coffin. All of it happens before the driver even has time to understand what has failed. So how did Mercedes-Benz, a company known for building seemingly immortal engines and teaching the world new safety standards, become associated with a rusting chassis and suspension parts tearing away from the body? And what if the real cause was not simply age or bad road conditions, but a cost reduction decision made years earlier on a design table? I am Halil Ibrahim, a mechanical engineer with 10 years of experience and a quality manager in the automotive industry. In this investigation, we will examine how Mercedes-Benz's obsession with engineering first created a legend and then helped lead the company toward a corporate quality crisis. And we will do it through technical evidence, not nostalgia. When investigating the root cause of an accident, we examine not only the broken component, but also how the vehicle behaved just before the failure. This is where the EDR, or Event Data Recorder, becomes important. This electronic black box records wheel speeds, engine torque, steering angle, and sudden transient deviations. A transient deviation is a temporary change that disrupts system balance. In the chassis, these load transfers help us reconstruct the sequence of the accident. The data leads us toward an uncomfortable possibility. The problem may begin not on the road, but much earlier, in design and material decisions. The irony is that Mercedes was once criticized for the opposite reason. It was not accused of cutting too many costs, but of placing almost no limits on engineering. To understand where that crack began, we need to return to 1986 and Stuttgart's great V12 panic. In the final months of 1986, news from Munich alarmed Mercedes management. BMW was preparing a V12 engine for the new E327 series. For a company that had treated luxury and engineering supremacy almost as a natural right, this was more than another competitor's engine. It was a direct attack on the throne, and Stuttgart immediately understood the scale of the threat. The W140 project was already approaching launch, but it was stopped and pulled back into development. Chief engineer Wolfgang Peter's team was no longer expected merely to catch BMW, but to surpass it. The result was the M120, a 413 horsepower V12 for the 600 SEL. That decision delayed launch by 18 months. In automotive development, 18 months means rewriting the entire plan. Designing a V12 is not just a matter of placing 12 cylinders next to one another. Both cylinder banks have to operate on one crankshaft with extremely precise synchronization. Think of two orchestras playing on the same stage. If one conductor loses the rhythm, the entire symphony begins to collapse. Mercedes managed this balance with two independent ECUs, while forged steel solutions were developed to control torsional loads in the crankshaft. But the obsession did not stop at the engine. To isolate the W140 cabin from the outside world, Mercedes used double-layer acoustic glazing. The air gap between two thick panes reduced wind and road noise, while also improving thermal insulation. The glass became so heavy that engineers had to recalculate the torque capacity of the lifting mechanisms and the load carried by the door hinges. Even parking the 5.1-meter body became an engineering problem of its own. At a time when ultrasonic parking sensors were not yet common, selecting reverse gear caused two 65mm chrome guide rods to rise from the rear corners of the trunk lid. Looking through the mirror, the driver could physically see where the body ended. And this was the core problem. Mercedes was no longer simply developing a car. It was trying to defeat every inconvenience with engineering. When the W140 was finished, it became one of the world's most ambitious luxury cars. But the board saw a darker picture. The R&D budget had reportedly deviated by around $1 billion, and the car emerged roughly 25% above its planned unit cost. Engineers called it perfection. Finance called it uncontrolled cost. Inside headquarters, one sentence began to circulate. One day, this quality will bankrupt us. The battle was no longer only against BMW. It was developing inside Mercedes, between engineers and accountants. Yet the engineers were not ready to surrender. Their response would not be a management presentation. It would arrive on the road, hidden inside the body of an ordinary W124. The argument had moved from spreadsheets into philosophy. How much engineering was enough, and who would be allowed to decide? And here it is, in all its glory, the W124-500E, quiet from the outside, but carrying nearly the entire engineering stubbornness of that era underneath its familiar sedan body. From a distance, it looked like an ordinary family sedan, but Mercedes wanted to install the M119, the 5.0-liter V8, from the R129 SL inside that body. The problem was not its power, it was its size. The standard W124 had been designed around narrow inline-4 and inline-6 engines. The M119, with two wide cylinder heads, almost filled the engine bay. Imagine moving a grand piano through a narrow hallway. You either give up on the piano or change the walls. Mercedes chose the walls. The front suspension towers, chassis mounting points, and firewall area were redesigned. Tolerances became so tight that a few millimeters of deviation could create a collision with another component. But fitting the V8 was only the first problem. To put the torque onto the road more effectively and improve stability, the track width was increased by 56 millimeters. That required wider fenders, additional bodywork, and changes to the lower structure. Then came the unexpected part. The new body no longer fit Mercedes' own production line. The standard welding robots in Sindelfingen could not properly handle the widened body shell. Mercedes had effectively designed a Mercedes that could not be built inside its own Mercedes factory. Under normal conditions, the answer was obvious: reduce the design. The engineers refused. Instead, Mercedes reached an agreement with Porsche and created one of automotive history's strangest production flows. Raw bodies left Sindelfingen and traveled about 20 kilometers to Porsche's Roßlebau facility in Zuffenhausen, where widened fenders and structural modifications were completed largely by hand. The body then returned to Sindelfingen for painting in Mercedes' own paint facilities. After that, it went back to Porsche, where the M119 V8, suspension, and running gear were installed. Finally, for quality validation and dynamic testing, the completed car returned to Mercedes again. A single 500e needed around 18 days to complete this production cycle. To a financial analyst, this was an efficiency nightmare. To an engineer, it communicated a completely different principle. If building the right car means changing the production system, then change the production system. That is how the 500e was born. Traveling between Mercedes and Porsche, finished with extensive handwork and surviving despite the growing internal war over cost. But this was not a new reflex. Mercedes had been fighting limits for decades. The roots of that mentality go back to a racing car that once rolled onto a scale just 1 kilogram too heavy. The date is June 2nd, 1934. Nürburgring. New regulations limited cars to 750 kilograms, excluding fuel and tires. The Mercedes-Benz W25 weighed 751. Just 1 kilogram, but enough to erase months of development in a single measurement. Team manager Alfred Neubauer refused to accept it. That night, mechanics stripped away the white paint with blades and sandpaper. By morning, roughly 1 kilogram had disappeared. The W25 returned within the limit and went to the track with its bare metallic body exposed. That was the birth of the Silver Arrows legend. But Mercedes' greater confrontation with physics came 4 years later, on the Frankfurt-Darmstadt Autobahn. On January 28, 1938, Rudolf Caracciola sat in the W125 Rekordwagen. Ahead was a long, almost empty highway. Behind him, a twin-supercharged V12 producing roughly 736 horsepower. At these speeds, however, the main enemy was no longer the engine. It was the air. Aerodynamic drag grows according to this equation. Velocity is squared. Aerodynamic drag rises brutally as speed increases. Mercedes therefore pushed the W125's drag coefficient down to about CD0, 0.157. The compromise was extreme. Conventional radiator openings were closed because every opening created additional resistance. That created another problem. How do you cool a 736 horsepower V12 while refusing air to the radiator? Mercedes answered with something almost absurdly simple. The car carried roughly 500 kilograms of ice and water. Engine coolant circulated through this thermal mass, and the ice absorbed the enormous heat for a few critical minutes. The system was not designed for continuous operation. It only had to survive one record attempt. The tires were at their own limit as well. Continental reduced tread thickness to around 1.5 millimeters to lower the risk of centrifugal force tearing the surface apart. Caracciola was racing against two invisible clocks: accelerate before the ice disappeared, and lift off before the tires reached their structural limit. Every second was a thermal and mechanical countdown. The result was 432.7 kilometers per hour, a public road record that remained unbeaten for roughly 60 years. 1 kilogram of scraped paint had evolved into half a ton of ice, fighting the limits of physics. But Mercedes' obsession with defeating physical limits was soon pulled into a darker world. By the late 1930s, speed had become more than an engineering objective. It was also propaganda. Behind the record boards stood a political demonstration of industrial power. One of the most extreme machines of that era was the Mercedes-Benz T80. Designed by Ferdinand Porsche, this roughly 8-meter-long, 6-wheeled silver machine had one extraordinary target: 750 kilometers per hour on the Dessau Autobahn, a number intended to demonstrate German industrial power to the world. Under the body sat nothing resembling a normal car engine. A 44.5-liter Messerschmitt DB603 inverted V12 derived from aircraft technology. Target output was around 3,500 horsepower. Ordinary gasoline was not enough, so the planned fuel was an aggressive cocktail of methyl alcohol, gasoline, acetone, nitrobenzene, and ether. A serious deviation in fuel pressure or mixture could push internal components beyond their thermal limits in seconds. The T80 was an astonishing engineering machine, but it never reached the highway for a real record attempt. It was 1939 and war had begun. A machine designed for 750 kilometers per hour was quietly locked away before it could prove itself. Only a few years later, Stuttgart faced the opposite problem. Yesterday, the discussion was how to reach 750 kilometers per hour. Now the calculations were about survival. The question was no longer, how fast can we make a car go? It had become, how can we make a car move when there is no fuel? By 1942, war had torn apart the production system in Sindelfingen and Stuttgart. Factories were being bombed. Oil supply lines were collapsing. Raw materials were disappearing. Production had also become part of a brutal wartime economy that made use of forced labor and prisoners of war. Civilian fuel had almost vanished, and engineers who had once worked on sophisticated injection systems were now being forced to attach enormous metal boilers to cars. The system was called Holzgas, wood gas. With refined fuel unavailable, engineers effectively had to turn automobiles into rolling furnaces. The driver filled the metal generator with dry wood or charcoal and heated it under restricted oxygen. Instead of burning completely, the material was gasified, producing a combustible mixture that included carbon monoxide and hydrogen. One of the basic reactions was the gas traveled through pipes into the intake manifold. The cylinders were no longer fed with gasoline, but with gas produced moments earlier inside a boiler full of burning wood. It worked, but the penalty was severe. Wood gas had far lower energy density, volumetric efficiency dropped, and engine power could fall by roughly 60%. A 100-horsepower engine could become a 40-horsepower machine. Throttle response also became painfully slow. Pressing the accelerator opened the throttle, but gas production inside the generator needed time to increase. This delayed response could lean out the mixture on hills, cause the engine to struggle, or even make it stall. Only a few years earlier, the same engineering culture had carried half a ton of ice to reach 432 kilometers per hour. Now it was burning wood simply to make a car move. On one side, a V12 cooled with ice for a speed record. On the other, a civilian car carrying a boiler. Few contrasts show more clearly what war did to engineering. When the war ended, the rusty generators disappeared. Engines became powerful again. Racing circuits reopened. Mercedes returned to motorsport with years of suppressed ambition, almost as if it wanted to recover everything at once. This time, it returned with a machine that seemed close to engineering perfection. And precisely for that reason, the price of what happened at Le Mans in 1955 would be even more devastating. The machinery had recovered, but the memory of scarcity had not. Mercedes returned to the track, carrying both technical confidence and the weight of everything the war had interrupted. June 11, 1955. We are at the Le Mans circuit. As the clock approaches 1828, racing cars pass the grandstands at close to 250 kilometers per hour, only a few meters from the spectators. Engine noise shakes the stands. Mercedes has returned from the ashes of war and is determined to prove once again that it can build some of the fastest machines in the world. Pierre Levege is behind the wheel. Under him is the 300 SLR. From the outside, it looks like an elegant silver race car. Lift the bodywork, however, and you find a mechanical laboratory. The engine was designed not only for speed, but to survive extreme RPM. At its heart was an inline-8, and Rudolf Uhlenhaut attacked one of the great high RPM problems, valve float. Think of compressing and releasing a spring too quickly. Eventually, it can no longer follow the motion. Inside an engine, if the valve spring cannot close the valve in time, the rising piston can strike it and destroy the engine within milliseconds. Mercedes' answer was a desmodromic valve system. The valve was opened mechanically and closed mechanically. Removing dependence on spring inertia allowed operation beyond 8,000 revolutions per minute, while Bosch mechanical direct injection delivered fuel straight into the combustion chamber. On paper, it was extraordinary. Yet one of the greatest advantages of the 300 SLR also carried one of its most dangerous weaknesses. To reduce mass, parts of the body used electron, a magnesium-aluminum alloy. Magnesium is light and strong, but under the wrong conditions, it can burn with terrifying intensity. At 1828, Levegue's 300 SLR made contact with the Austin Healey ahead at roughly 240 kilometers per hour. What followed took seconds. The Mercedes launched into the air, broke apart, and threw components toward the spectators. The mechanical roar of the circuit became metal, fire, and panic. Then the silver body disappeared behind a blinding white magnesium flame. Now let us place the wreckage on the table like quality professionals. We need to understand not only the collision, but the material behavior after impact. Why was the fire so difficult to control? Burning magnesium-containing components behave very differently from ordinary structural materials. At critical temperature, the reaction can become extremely intense and self-sustaining. When very hot magnesium interacts with water, hydrogen can be released. So under the wrong conditions, something normally used to fight fire can make the situation worse. And this is one of the most dangerous patterns in engineering. Optimizing one parameter so aggressively that another risk becomes invisible. Less mass, more speed, better performance. But the way a material behaves during a crash belongs to an entirely different world. 84 people lost their lives at Le Mans that day, and Mercedes later stayed away from top-level motorsport for decades. But another engineering philosophy grew stronger from the wreckage. Béla Bareigny's principle was simple and radical. Do not protect the car, protect the human being. The front structure should deform through crumple zones and absorb kinetic energy, while the passenger compartment should remain as rigid as possible as a survival cell. Mercedes was no longer asking only, how do we go faster? Another question mattered just as much. When something goes wrong, how do we keep the human being alive? The irony was that every better answer made the cars safer, more durable, and more expensive. Years later, people in Stuttgart would decide that this cost was becoming unsustainable, and that takes us back to the W210 lying on the highway. That shift would define the next era of Mercedes engineering. Performance would still matter, but survival would become part of the design equation itself. So we return to that night. Back to the W210 collapsed onto the road. The sparks from the opening are no longer just an accident image. They are the final visible link in decisions made years earlier. This time, we ask not only what broke, but why the system allowed it to break. Metal does not make decisions. Someone chooses the material. Someone defines the coating. Someone reduces a safety margin to save a few cents. That is how these stories begin. When Jürgen Schrempp took control of Daimler-Benz in 1995, Mercedes' management philosophy began to change. A company long dominated by engineers increasingly turned toward a Wall Street concept, shareholder value. A component surviving for 20 years was no longer the only definition of success. Delivering the same function more cheaply was also success. Sometimes those two objectives become enemies at the same table. Return to the W210 front wheel arch. The steel perch carrying the coil spring reads like a metallurgical record of corporate compromise. In the search for small savings per vehicle, corrosion protection became a critical vulnerability. Galvanization, or zinc protection, was central. Wherever steel lacked sufficient zinc coating, it was left far more exposed to corrosion. Another weakness existed around welded areas. Water and moisture from the wheel arch could collect around these joints. Once unprotected steel met water, electrochemical oxidation began. From the outside, rust can look cosmetic. Here, however, corrosion could progress beneath the surface and slowly reduce the effective cross-section of load-bearing steel. You might see a few brown marks while structural capacity disappears underneath. Every pothole, every braking event, every corner, each adds another load cycle to the spring-perch. Metal fatigue is dangerous because the final break looks sudden, even when failure has been developing for years. Eventually, one final load cycle arrives. The sheet can no longer carry the spring force. The perch tears away, and the 2-ton fortress from the opening collapses onto the road. That is why corrosion around W210 body and suspension areas became so symbolic. The issue was never only rust. It was the erosion of a century-old perception of reliability. The engineering culture that once scraped paint through the night to save 1 kilogram, carried half a ton of ice for a speed record, and sent a V8 sedan back and forth to Porsche rather than compromise the design, was now calculating savings measured in cents. The pendulum had swung to the opposite side, but the story did not end there. As the 2000s began, cost pressure moved deeper into the engine itself. And next time, the component that failed would not be a spring perch. It would be the timing chain itself. We will open that new file in the next documentary. Until then, take care.